Hi, Brian Miller-Hicks here, talking about engineering geology. I'm going to tell you about laboratory testing. Very important, very crucial step in any soils and geologic investigation. You've been to the field, you've done your investigation, you've dug holes, you've taken samples from backhoe test pits or borings. Now you're going to take some of those samples back to the lab and test them. Basically, what you want to test them for is their material properties like strength, moisture, density, and you also want to find out what their texture is, whether they're clays, silts, or sands, so that you can classify the soils. All these properties are crucial in determining foundation types, the type of mitigation or soil improvements you may have to undertake. So the laboratory is the next step after the field, in between field investigation and report writing. So this shows a laboratory test in progress called a compaction test or a Proctor test, wherein layers of soil are placed in this mold. This cylinder is actually a hammer that's a piston hammer, so you bring the piston up in a hollow tube and then you let the piston drop and pound the sand, if you will, pound the material in this mold, which is a 4-inch diameter standard Proctor mold. And you do this, I was trained to do it in 5 lifts or 5 layers. Each layer was pounded 25 times by this weight here. I forget the actual weight of the weight, but so each layer is 25 times, and you bring it up, bring it up, bring it up, and then you come out with a molded, compacted cylinder of soil, and you weigh that and determine its moisture and determine its density. So you want to do, for any specific type of soil, you want to do this 3 times, at least 3 times. Once with a soil on the dry side, once with the soil near optimum moisture, and once with the soil at a wet side, more saturated moisture. That way you get a curve, which I'll show you a little later in a subsequent slide, what I'm talking about. Okay, so why do we test samples? And primarily in geotechnical engineering, most structures are actually built on soil rather than rock. So we tend to pay more attention to tests which are run on soil and not bedrock. Bedrock, of course, is much denser, much stronger. So the main qualities of strength, or the main qualities of rock mass that we want to look for, are fracture patterns rather than actual density and moisture and strength. So we do a lot of tests on soil samples. We want to classify the soil. We want to determine its texture, whether it's clay, silt, or sand. Its natural density, is it dense out in the field, or is it loose, or is it medium dense? We have to determine that. And here's the Proctor curve that I was talking about. You want to find the maximum density of the soil at optimum moisture for fill compaction. In other words, you take a soil and you compact it or engineer it out in the field to be ready to accept the stresses of structures and foundations. You want to bring it to that maximum density to determine whether it attains maximum density at 12% moisture or attains maximum density at 15% moisture. That's why you run these Proctor tests, and the first slide I showed you with pounding the soil in that steel cylinder. You want to, of course, determine its natural moisture. Then you want to determine its strength, shear strength, compressive strength, its cohesion, if it's a sand, it's got low cohesion. If it's a clay, it's got high cohesion between particles and grains. The angle of friction is also a measure of strength. Generally speaking, clays have a lower angle of friction, a less steep angle of friction than sands do. Plasticity, that has to do with whether it's a moldable soil like a clay or non-moldable like a sand. Expansiveness, this can be critical in some soils and areas. There are certain clays where if you add water to these clays, the soil will actually swell or expand. So you want to determine that if that's going to be a factor during your construction. Consolidation, some soils actually compact or consolidate and lose volume under loads. Some soils, for example, in East County area of San Diego, are very porous and dry in their natural state. If they're subject to additional water from irrigation or swimming pool leaks or what have you, sources of moisture, they can actually collapse. And we can measure the degree of collapse or consolidation in the lab. I'm not going to go through this chart in a lot of detail, but this is our unified soil classification system developed in the early part of the 20th century. Mainly, I believe, by Dr. Tajagi. So soil classification is based primarily on size and plasticity. Size going from top to bottom. These are the coarser soils up near the top. So you have gravels, silty gravels, clay gravels, sands, clay sands, for example. And then you jump into the clays down here, silts and clays, silty clays, clay silts, inorganic clays, organic clays. Each of these symbols, ML, CL, GW, SW, represent a different type of soil based on their particle size and based on their cohesion, whether they're clays or sands or silts. Okay? It's important to classify soils that you bring back in the lab from the field. Here's a photo showing, that's not my hand, but showing somebody's hand feeling the soil. You can get quite a bit of information when you're out in the field and you're just looking at the soil, picking up a handful, rolling it around in your hand, seeing how wet it is, seeing whether it's a sandy soil and it's coarse or rough, or if it's a smooth, silky soil like a silt, or a sticky plastic soil like a clay. So you can do this in the field and you learn from experience what soil is what. So you can pick it up, don't wear any gloves. I've seen engineering geologists, soil technicians, and engineers out in the field wearing gloves as they handle the soil. Not sure why. Maybe they're afraid of getting germs from the soil. I've handled many hundreds, if not thousands, of soils through my career, and I have no problem with it. You can feel it, roll it, smell it. Smelling you can detect organic odors or other odors. Put a little bit of it between your teeth. If it's gritty, it's got sand in it. If it's not gritty, it's a silt or a clay. You can determine density and hardness, general relative stiffness, plasticity, whether it's clay. If it's a clay, it can be plastic. If it's a sand, it's not plastic. And of course, color is very important. An oxidized soil will be orange or reddish in color. A gray soil will be a reduced type depositional environment, gray or gray-blue. So you can use the Munsell color chart or not. You can describe a soil simply as red-brown or yellow-brown or blue-gray or gray-green. Those are generally adequate for field descriptions and descriptions in your logs. And of course, you want to get a general idea of what the moisture is. So here's a picture showing how you do field texture classification. You pick up a bunch of soil in your hand, feel it and squeeze it. A cast will form if it's moist. Then you, with more silty or clay soils, you can actually mold it and roll it around in your hand. A very clay rich soil you'll be able to form a rope or a ribbon that can roll around, and you can keep rolling it around till you dry it out, and then it starts to crumble. Then it's reached what we call a moisture limit that I'll talk about a little bit later. So sands can be formed into just lumps or clumps. Clays can be formed into balls of material or ribbons of material. So here's a USC, Unified Soil Classification based on particle size characteristic, sand, silt, clay, liquid limit, and plasticity index I'll talk about in a little bit. And how do you get a test for particle size characteristics? Generally speaking, a soil will have many different size particles in it. It's pretty rare when you get a soil that's got a uniform size to its grains. An example of that type of soil might be a very well sorted, poorly graded sand on a beach that's formed primarily of quartz grains, which can be more or less the same size. But generally speaking, most soils are composite particle size. For very fine grained soils that have clays, you can run a hydrometer test after a sieve analysis. Liquid limit, plasticity is called Atterberg limits. I'll explain all that coming up. So you're inside the lab. You got your soil samples. One of the vital pieces of equipment you must have in your lab is a scale to weigh stuff. Obviously, you cannot get a moisture or a density of soil without weighing it. Here's the laboratory oven. You put samples in the oven to get their moisture content. Another indispensable piece. So let's classify soils. How do we do that? The first way is by determining their distribution of particle size. Okay, back to the Unified Soil Classification System. Coarse soils up here, fine soils down here. So we can set up a stack of sieves. This shows 3 inches, 2 inches, 1 inch. So that means that the space between the mesh is rather large. The space between the steel mesh filaments or strands, I guess, in this sieve is 3 inches. That's really big. It means most soil will go right through that, and you'll only catch the big rock. So some rocky soils, you may have to use these large space sieves. Then as you go down the column, the spacing between the wires gets smaller and smaller and smaller. The smallest one we typically use is called a number 200 sieve. So any soil that passes through the number 200 sieve, you will treat differently. That means it's clay size. Okay, so you've got that all sorted out. You've got over here percent passing. So up here you have the largest sieve. So here's particle diameter. It's not sieve number, but particle diameter is equivalent to a sieve size. So here you have a large particle diameter. 100% of your sample passed through that sieve. And here, only 80% passed through that sieve. So there's 20% left between here and here. Okay, and you go through each sieve and you determine how much soil is left, or how much soil has passed through each respective sieve, and you come up with a curve. And then you take points on the graph and you determine what type of soil it is based on its particle size distribution. Then the material that has passed through the number 200 sieve, the very, very fine stuff, clay size stuff, silt size stuff, you may run a hydrometer test to determine silt and clay fractions. Basically, you take a beaker of water, pour your soil passing the 200 sieve into the cylinder, and then let it settle out. The heavier silts will settle to the bottom, and the lighter clays will stay in suspension for quite some time. And then you can get the percent of silt and the percent of clay from this procedure. Okay, so you've classified your soil by particle size. Now you want to determine its plasticity from a procedure we call the Atterberg limits, liquid limit and plasticity index. So what you do is get a wet sample of that soil, put it into this brass bowl here, as you see here, then crank that bowl. As you turn the crank, the bowl goes up and down, up and down. As you crank it down and it impacts the hard rubber base, it will start to flow. So you have put a groove down the center using a grooving tool. And as you bang it up and down, some amount of soil actually starts to flow into that groove. You measure that, you take a half an inch. If it's floating in about a half an inch, then you can scoop out a sample of that soil, weigh it, and get its moisture. And the difference in moisture content will give you your liquid limit and plasticity index. Sorry. So here is a plasticity chart. So the point at which you have taken that soil that's flowed into that groove, let's say it is, hang on a second, 31% moisture. I'm sorry, let's say the moisture of that liquid flowing soil is actually 62%. Then you take some of that soil and you rub it between your hands, form rolls, keep rolling it until it dries up and breaks up. That is your moisture content on the dry side. So the 62 minus the 31 in this case would give you a plasticity index of 27. So you plot those data points. Here's 62 and here's 27, and that puts you square into the organic silts side of this graph. Okay, that classifies the plasticity of your soil. Why is that important? Well, gradation, here's one example of why it's important. It relates to liquefaction. And liquefaction, as you know, is the phenomenon when during an earthquake, saturated loose sands can liquefy and lose volume and cause above ground structures to actually settle. So it's important to understand the gradation of the soil, whether it's a granular soil, and it occurs when you have liquefiable soils at depths shallower than 15 meters below ground. Excuse me. Soils most susceptible have very low cohesion with a liquid limit less than 35%. Okay, so it's important to classify soils, especially if you're in a situation where your site is sitting above a high water table and you have loose saturated sands down below. Let's look at the other soil engineering properties like strength and density. Okay, so natural soil density and moisture is what you recover, what you determine from your field samples. This is a picture of a ring sample where you have brass rings that are put into a steel sampler. The sampler is driven into the ground and the soil ends up inside these rings. You take these rings apart and you can measure the weight and you can measure the moisture and you can get their natural density. Here's another way of doing it, a wax density procedure. You take that soil sample, you weigh it, then you coat the sample with wax, you weigh the coated sample, you submerge the sample in water to determine its volume of water displaced, and that way you can determine the density. Some strength tests. These are very commonly run in most soils labs. Unified compression test or uniaxial. Here's a cylinder of soils recovered by driving the sampler into the ground and recovering this cylinder of soil. Then stress loads are imposed vertically on this sample until it fractures or breaks, and you determine that load that the soil took and you convert that to a strength based on the load failure, load at which it failed. Same kind of thing can happen here, only you're not displacing vertically, you're displacing laterally. These are commonly used in most labs to get a strength factor, to determine cohesion and coefficient of friction. And they're especially critical when you're, say, dealing with landslides. You want to get a sample, if possible, of the slide plane material and test its shear strength. The shear strength should be low with a angle of friction of 6 or 7% and a high cohesion. Okay. Here are other tests. I mentioned expansion with swelling clays. So this is kind of the opposite of a compression test. You put a sample in a metal container. And then you saturate the sample. And as the soil swells, it will move this piston upwards, and the amount of swelling will be recorded on this dial. And sort of the opposite of the expansion is a consolidation test. As I mentioned, there are some soils which collapse or consolidate with additional moisture. So you load the samples into these brass containers, fill them with water, and then impose additional loads and add water if you need to saturate them further, and that will give you a degree of consolidation, amount of consolidation or volume change or reduction in volume it has undergone under loading. Here is that compaction test that's illustrated by my first slide. Modified Proctor test, let's see. Yeah, this is the one I'm familiar with. A 10-pound hammer with a falling height of 18 inches, 5 layers. So each layer gets 25 blows until you get a solid compacted cylinder of soil, which you then take out, measure the weight, measure the moisture, get its density. So as you see from this curve, if you're on the dry side, here's a moisture content, 4.5% moisture, and you undergo the compaction testing. It's got a dry density of 140 pounds per cubic foot. If you add moisture, if you add too much moisture, if you go up to 8.5% moisture, it's got a very low density of 142 or so pounds per cubic foot. But if you get the moisture just right, not too dry, not too wet, just right, that's where the soil will achieve its maximum density way up here at 145. So when you're handling fill at a building site and you've excavated soil and you want to pack it into an area that will receive a structure, you want to compact that soil to its maximum density. So you want to compact it at optimum or near optimum moisture to make sure it achieves this highest density. And the rule of thumb, the standard is you want to achieve at least 90% of that optimum or maximum density in the field through compaction by rolling over it with heavy equipment or using mechanical rollers or sometimes even jackhammer type devices that can be manually used by an operator. So this is just an example of lab results page in a report. So here we have maximum density, optimum moisture. Our maximum density for this silty sand was 120, optimum moisture 9.6%. For the clay sand, we have a lower maximum density of 124 and a higher optimum moisture of 10. Here's our expansion indexes for various soils, ranging from 17 expansion index, which is very low, all the way up to 98, which is very high. Corrosion, these are primarily chemical tests for pH, acidity, chloride content, and sulfates content. Some of these, the corrosion tests are run on soils to see whether the soils will corrode metal structures like culverts, pipes, beams even. So if they are shown to be corrosive soil, you can undergo some chemical modification or replacement of these soils. So to summarize, here's our test result applications. Field identification, sieve, hydrometer, Atterbergs, that's soil classification. Density and moisture, strength and moisture considerations. Unconfined compression, direct shear, soil strength. Swelling soils by means of the expansion index. Settlement or collapse potential by means of consolidation test. And you base your fill control and testing of compacted fill in the field based on the results of your proctor test. Thank you for watching. Talk to you next time.